What is up, current tech fans? Welcome back to another garage tinkering video. This is going to be quite an important video because it's going to bring everybody up to speed to ensure that as we move forwards on this channel, everybody kind of knows how the basic processes of creating digital displays for your car work. So what we're going to do in this video is the entire process from actually just very quickly analyzing the data that is being sent from the car with a little bit of CANBus sniffing through to taking that CANBus data, broadcasting it through ESP now to a display, and that display is going to output that information, and we're going to look at the various different forms of information, ranged, big and little endians, a byte data, and a single bit data point, which if you don't understand, good, because by the end of this video, you will. So we'll start this journey inside the car in the CANBus. Now, not every car has a CANBus, but anything from the last 30 years probably does. And a CANBus is a CAN bus, a controller area network bus. And if you're not aware of what a bus is just a series of interconnected devices, typically within a computer or a system. And in your car, you likely have a number of different computers that control different things. You might have the body control module, which controls things related to the body of the car, and the engine control module, and an ABS control module. And they're all individual computers with specific tasks. And what these things do is process information, listen to sensors, all that kind of stuff. And when they have information that the other computers need to know about, they send it out onto the bus. And it sends it out onto these two wires, a CAN high and a CAN low, which connect to the CAN high and CAN low of all of the other computers. And then the devices that need to receive that information do so, and the ones that need to ignore it just ignore it. So instead of needing to have lots of individual connections between the different computers that want to talk to each other, we just create a single network, and that is the bus. And you can think of it like a bus route. When we talk about the CANBus, that's what it is. It's the interconnected series of little computers that control different things in your car, around your car. So CANBus sniffing is the ability for us to listen to all of that traffic and pick out the bits of information that we want. Unfortunately, the majority of modern cars have a diagnostic slot, the OBD2 port, and all of the traffic routes through that OBD2 port, which means we can listen to it, and using an Arduino and a device like this, we can then take that information and utilize it. So that's all well and good, but how do we actually get that information? And there are typically two ways that we can connect to the CANBus, and then two ways that we can distribute it. The easy way and the harder way. The easy way is using that OBD2 port and putting in a device much like this. Now, this is the OBD2 shield created by fellow YouTuber and automotive parts manufacturer, Mr. DIY. This is very, very good. I have several of these now, and what they do is plug directly into your OBD2 port. They have a bunch of stuff on the board for power management and protections and all that kind of stuff, but most importantly, there is a CANBus transceiver which will listen to all of that CAN high and CAN low signal traffic and read it in the ESP-32. Then what you use one of these ones for is to distribute that information wirelessly, which it does using the protocol ESP now. And then your other devices can have another ESP-32 on them that also has ESP now, which listens for that incoming data. Basically, you're just creating a connection between two devices in a wireless format. When you're prototyping and making things, this is by far the best and the easiest way of doing things. You don't have to go and hack anything up in your car. It's a lot safer that you can put protections in place, like you can put this into a read-only mode, so you're not going to accidentally cause any damage to your car. It's a super safe way of doing it, and yeah, definitely the way I recommend, especially if it's your first time. These are readily available. I will put a link to Mr. DIY's shop down below where you can go and grab these if you want. I do thoroughly recommend them. But when you've finished all your prototyping, you might not want to have one of these stuck out of your OBD2 port all of the time, and you might not want to rely on wireless communications for things that are safety critical. Let's take speed, for example. If that wireless connection goes down and your speedo drops out, that's a problem. So we might want to actually utilize something that's a little more robust and a little bit safer. What we can do instead is connect directly to the hardware CAN, probably somewhere up behind the dashboard. You find the wires and you connect to it directly with a new pair of wires, which go into a hardwired CANBus transceiver on an ESP32 board that you're using. And then again, we can manipulate that information and send it to our boards via one of a number of processes. We can create a private micro CAN, we could use serial, we could use, again, wireless. There are lots of different options. So we've managed to listen to the car's CANBus and hear all of the data, and then we need to filter through it. So we can either do that on the sender or the receiver, depending on our setup. Typically speaking, if we're using wireless and ESP now, we'll filter before we send, which keeps the ESP now requirements of sending so much information a bit lower, because ESP now is very system intensive and will have a tendency to slow down your screens if you do too much sending. So we'll filter before we send, but if you're doing hardware CANBus, you might just filter after you send because it can handle it a lot more easily. And then we want to display it on the screen somehow. So we're going to need some form of hardware. There are a couple of options for this. Now, personally, I'm in the process of creating my own perfect gauges, and I want a 2.1 inch gauge which doesn't have touchscreen on it, because I don't feel like touchscreen is particularly good in cars. So I have a perfect board that I'm working on, is actually available for pre-order from next week. If you're interested in registering interest for these boards, if you click on the register interest link below, you can find a form that you can fill out, and I can let you know when the boards become available. But we'll look at them more in the next couple of weeks. Otherwise, a popular choice is this 2.1 inch LCD screen by Waveshare. It uses basically the same chip. It's got a lot of the same setup, and you can utilize the code that I wrote for this board, which has been deliberately made a lot more minimal and easy to understand than sometimes the example code that comes with this screen is. You will have to change one bit. I'll talk you through that when we start looking at the code, but we can do it on these screens as well. If you don't want to wait around several weeks for my boards to finish prototyping, these Waveshare 2.1 inch touchscreen driver boards will do the job just as well. So using these boards and the code that I'm going to talk you through in a minute, we can display LVGL, which is the Light Versatile Graphics Library. It's what we like to use on this channel to create displays for these things. It makes life a lot easier. Then we're going to take that filtered information and then use it to update the values, and if things are switched on and off, or arcs, or whatever it might be on them. Once we've got to that point, we're taking information from the car, we're broadcasting it in some way to our screens, and our screen is updating based on that information that's coming in. That's our entire end-to-end process done. Now, obviously, there's a whole other step about how do we make containers for it, or display it in the car, or power it in the car. These are all other concerns and things that we are talking about on this channel quite a lot. But this video is really, let's get everybody up to speed. So now that you kind of know the process of the whole thing, let's dig into it a bit more, because there are obviously a lot of important steps along this process that you need to understand. So we'll start with the car and CANBus sniffing. There are a number of different types of these CANBus shields and distributors out there. Like I say, I like to use the one by Mr. DIY. Find it works very, very well. And one of the good things I really like about it is its ability to set itself up for broadcasting everything to SavvyCAN. If you're interested in this whole process, SavvyCAN is an application that you're going to have to get familiar with. What it is a CANBus sniffing and data propagation tool that allow us to capture and analyze data coming from any CANBus, but in this case from the car. If you're using the Mr. DIY Shield, you can literally just hook it up to your computer, go to this page on his website, click the online flasher, and put the code onto it that is required for just powering SabiCan in its kind of like live analysis mode. Makes it super easy. It's the way I always do it when I want to put that code on the device. Once we have that code on the device and we have SabiCan running on our laptop, we're ready to go and just find the first few bits of information. And we're not going to do a real deep dive into finding all of the different kinds of information that come from a car CANBus. There is tons of information about everything that's going on in your car, but we'll touch on a couple of things that you can see the different kinds of information that come out of the car CANBus. Sat out in my frankly beautiful 350Z, we're going to start listening to some of the information and see what it has to tell us. The broadcaster is plugged in, the laptop is on and connected to it. If you need a breakdown of how to connect a laptop to this thing and listen to all this wireless data, Mr. DIY has a guide. It is linked below. You can see all of the information that's coming in from the car, and there's not a lot at the moment because I'm sat in the car, it's off, the keys are not in. So there's not a lot of information that's coming through. But as soon as we put in the keys, we start to get a bunch more information. And when we start it up, we get even more. So this is all of the information that comes out live from the car, and it's all the stuff that we're interested in. So the art of CANBus sniffing, and it's not something we're going to go into a huge amount now, but the art of the CANBus sniffing is being able to look at this information and find the key bits that we're interested in. So for example, I want to add left and right indicators to this example gauge. So if I turn my indicator left, we look for a data point that is changing as that tick, 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 tick happens. And we can see one here, and we notice that this is changing between these two values. So there's a fair likelihood that that piece of data is where the left indicator is being done. And then if I go right, we'll see it changes to a different number. Now we're going to take a look at what these numbers actually mean very briefly in a minute. But what's really important is we identify the ID of the block of information that we care about, and then we understand which byte and which bit position each piece of information is at. What I recommend if you want to do this is you can sit in your car and flash and flick and change all your different things and look out for the bits of information that are changing. That's a great way of doing it whilst just sat out on a driveway like this, but it won't allow you to analyze it when you're sat back inside your house or wherever you're doing your work. So what I recommend is go for a drive, let your car get up to temperature, do a load of things, indicate, flash your lights, do a bunch of stuff, take your windows up and down. But whilst you're doing it, record the drive, record the data, and then you can sit and analyze it afterwards, which is a much easier way of doing it. And it's a lot safer than trying to look at laptops whilst you're driving around. We're not in Fast and the Furious. So we spent some time sat in the car analyzing the information that we're extracting from the CANBus, and we've successfully identified a number of bits and bytes that pertain to the information that we want to display on our screens. How do we then filter that out of all the data and broadcast it correctly to our displays? Let's go look at our first bit of code. Like I said, I'm not going to dig too much into SabiCan and CANBus sniffing at the moment, but if we take a little glimpse at an historical drive that I went for in the car, this is all of the various data points that I have loaded up. And if I use the, let's say the frame data analysis window, we get to see all the different IDs that control different things around the car. And typically things are all together. So your various lights, for example, I know that my lights are here. They're in 60D. And you can see if we zoom out, this is over the course of the drive, things happened here and different things went on and off. And we can see that these ones just jump up to certain values. I know, because I've spent the time extracting it, that these are the indicator values. So when it's here, it means the left indicator is on. When it's here, it means the right indicator is on. When it's here, it means both the left and the right indicator are on, aka it's in flashing emergency mode, which means these values relate to a single bit of information, a 1 or a 0 that is turning on and off somewhere in the code, which determines whether or not that light is on. It's the same with the headlights, it's the same with the brake lights. They all are just a 1 or a 0, a on or off state. Sometimes, though, some information doesn't require just a single bit, an on-off. It requires an entire byte, so 8 bits, which means that it can hold a value typically between 0 and 255, but that can then be manipulated to have values outside of that range. One of those examples is coolant temperature. I've already done all the analysis that I need to on this car. I know where all the bytes are, so it happens that here on 551 is my coolant temperature, and you can see it starts down at 50-ish and it rises until it gets to a running temperature and then levels off. The thing is, this isn't actually a representation of what the actual coolant temperature was, because it actually started down nearer like 9 or 10 degrees. Because in the Nissan 350Z, this coolant value is actually offset by 40. So what I need to know is that it is this. If I delete all of these, we're looking for byte 0 on 551 offset by 40. So that's how we find the value that is held in a single byte, which allows us to, like I say, hold a value between 0 and 255. Some things that we pull out of the car, though, need to go to values higher than that. So numbers north of 255. Your speed, your RPM, good examples of them. So in order to do that, they use typically 2 bytes of information, where 1 byte offsets the other byte by a scaling factor. It's called a big or a little endian, and we can find them like this because, again, we know where they are. I know that my speed is in 354. We can see stuff that goes up and down here. It looks like it could be something speed related, and it's, if we remove all of these extra unused bytes, the 2 that we care about are these ones, 0 and then a modifier, which is the second one. If we look at this in a different view, we go to a graphing window, and then we right click and do a new graph. On here, we can say, okay, well, we know it's 0354. This one's going to be speed, 0354. And we're interested in the first 2 bytes of information. So it's going to have a data length of 16 from there. So these are the first 2 bytes of information that are being used together. It basically means that one of the bytes, instead of using them as 2 individual 8-byte segments, you use them as a 16-byte segment. So when we add that graph, we see they smooth each other out. So instead of being one like jumpy one and then one like little manipulator, they smooth each other out. And this is my speed. And in my drive on this, I went up to about roughly 40-ish miles an hour. So this is where it tops out, and it's around 6,000. So I know that this is actually in kilometers an hour. So I need to make an adjustment to this and do a scale. And the scale to go from kilometers an hour to miles an hour is you have to multiply it by the ratio, and it's 0.621. So there's 0.621 miles per hour to kilometers an hour. So if I change that scale to 0.621, this will suddenly come down to 4,000. So 4,000 is roughly 40 miles an hour. So I was a little bit under that. So then if I was to change this scale to that by a factor of 1,000 and add that, we can see now that my scale is correct. So this is an accurate representation of the speed that I did throughout this drive. So this is important information. We know our scale, but we also know our position of our bits. Now these ones are pretty simple to understand. It's 2 bytes, one after the other, and the first one is what's called the most significant bit. So this is a big endian. Sometimes you get them the other way around, where the most significant bit is the one after. So if we look for RPM, which again, I know where it is, it's 23D, And again, I'll just filter out a bunch of these, those two together. So our least significant byte, the one that's jumping up and down through the full range, is number 3, and it goes all the way up to 255, which is the max that a single byte can be. And then the one that is the most significant byte, the one that is then saying whether or not that is moving up or down through a factor, is number 4. This may seem confusing, and I think of all the things that we're going to do here, this is the most confusing thing. But once you start to get an understanding of what it is, it actually starts to make a lot of sense. But I'll show you this one on a graph as well, so you can understand it. The graphing window, we're going to do a new one, and this one can be RPM. And this ID is 023D. This one we want 3 and 4 to be our data, so bytes 3 and 4. But like I said, they've swapped which one is most significant. So we have to switch on little endian and then adjust that to there. So now it knows 3 is the least significant byte, 4 is the most significant byte. So when we add that, we get nothing for some reason. I've put in 32D, it should be 23D. So here is our RPM. But as you can see down the left hand side, it doesn't get very high. The RPM never comes up. Now I did a specific thing on this drive, and I know that when I tapped the thing here, I pulled it up to about 4,000 RPM. And I also happen to know from research and other people who have dug into making this analysis on this particular car that it uses a scaling factor of 3. So if I put a scale of 3 in here, basically tripling the value that is being read from the car, that is the actual representation of what the RPM is. So again, you can see it sits and idles just under 1,000, which is correct. You know, it idles about 850, but then when I tapped the accelerator whilst I was driving, it came up nearer to 4,000. So this is my RPM value. So that's a single bit, a single byte, and then a big endian and a little endian pair of bytes. So now that we've got the various forms of information that we want, bits or bytes or multiple bytes, we can filter them using our CANBus sniffer and broadcast it to our screens. If you want to follow this along or you want to build your own thing, I put this CANBus sniffer example code in a repo. You can download it from below. And really, it's just a basic setup that will allow you to pull out the bits of information that you want and then broadcast only the appropriate stuff via ESP now. So what we need to do is define what pieces of information we want to send to our screen, and we need to extract and process them accordingly and then send them on. So at the top, we've got our structure sending data, and this is the data that we're going to send to our screen. So what are we interested in and what format do they need to be in? We're going to do our speed in miles per hour. Am I ever going to do north of 255 miles an hour in a 350Z? No. So we can make it an unsigned int 8, which will give us 8 bits and mean that we can do a number up to 255. We're going to do our RPM. Our RPM will go much higher. So we'll use a 16-bit, which will give us a value of around 65,000 as the maximum number. Gives a lot more headroom for larger numbers. So that one can be our RPM. We'll do our coolant temperature, which is another 8-bit, assuming that nothing is going ridiculously high. We're not getting over 200 degrees Celsius. That means my car is basically about to blow up. So we'll call that coolant temp. And then we'll take 2 bools, so true-false values for indicating left and indicating right. So this is the structure of the data that I'm going to send to my screen. So what I need to do is filter through all of the CANBus data that's coming into this device, pick out the correct bits of information and manipulate it based on things like the scales and the biases that we figured out in SavvyCam. There are a bunch of helper functions that I've put into this demo file that you can use if you want. So we've got on data sent is it's one for ESP now, but because I'm sending information so quickly, 10 times a second, I'm not actually serial printing anything. It tends to slow down the sender. So just use it if I need to do some error checking. This is my sends data function. And at the bottom in the setup, I've created this task, which is send data, and it runs this send data function at my send data interval, which is, like I said, 100 milliseconds. So this thing just runs 10 times a second forever. And all it does is send ESP now, and it sends this sending data, which we've just established, to the screen. And it does that 10 times a second. It doesn't wait for anything. It just sends it off. We've got a couple of initializations. Obviously, we're setting up the screen as a peer in ESP now. You do need to update this screen address at the top with the MAC address of your receiving device. If you don't know how to get the MAC address of your device, there's a random nerd tutorial linked in the description below, which has got a snippet of code you can just drop on there and it'll tell you your MAC address. Then you save that in there. And we initialize the CANBus. If you're using one of the Mr. DIY CANBus sniffers, this will be set up and perfect and good for you to go. If you're not, you might just want to change these CANBus pins to whatever it is on your device. Maybe the data rate as well if you're not running at 500 kilobits per second, but most cars run at 500 kilobits per second. And then I have a couple of like helper functions. We'll discuss those in a minute, just for processing endians and bits. And I set flags in my sending data. You don't technically need to do this if you don't want to, but when I'm using a screen and it's receiving information from various different sources, you want to have a flag that allow you to switch between the structures of the data that's being set, because both the sender and the receiver have to agree on a data structure. And if those things are out of line, your data will get all screwed up. So you want to make sure that it's processing it with the right structure, and flags is just a nice easy way of doing that. And we'll touch on that more in future videos where we talk about multiple devices sending things to one screen. But for this, you can just leave it in, it's fine. The important thing is we come down to the loop, and in the loop we have our thing that's processing all the CANBus information as fast as it can possibly do, and we want to filter it out by various things. And we've got an example here. So if I just pull this out, so case 0354, which we've just looked at as being the speed of my car, and we're going to create a function where we process that speed. So this loop's coming through and it's going, if the ID is 354, then we process speed. So we need to create a function for processing speed. And by passing through this can message data byte, this isn't just one byte. This is all 8 bytes, or however many there are for that particular ID. It's all of them sent through. Sometimes there'll be 4, sometimes 6, sometimes 12. They do vary, but for the most part, they're going to be probably 8. So we can pass that through as a int 8 type. So in this byte data, we have all 8 bytes that we want to do stuff with. And like I said, it's currently in kilometers an hour. So let's make a couple of notes. In kilometers per hour. We also had to scale it down from 4,000 to 40. So there was a scale in there of 0.01. So we had to reduce it by a factor of 100. So our most significant byte was byte number 1. And our least significant byte was 0. So long as we know all of this information, we can then process it accordingly. So let's write out a load of variables that are going to be used during this processing. So let's say our speed least significant byte is 0. Our most significant byte is 1. We'll do a float of a scale, which is equal to 0.01. Yes, you could technically do that as an int and do it as 100 and then divide by 100 as opposed to multiplying by 0.01, but we're doing it this way. Then we have another float, which is the conversion, which is going to take it from kilometers per hour to miles per hour. So as we said, that is 0.621. And then we're going to do something that's a little bit of a safety thing with speed, because your car will generally slightly over-report your speed. So when your speedo says you're doing 70, you're probably doing 68, 69. It gives you that tiny little bit of a safety buffer. So we're going to put in, like I say, a safety buffer. And you might want to play with this value. But for me, I find that 2%, so timesing the number by 1.02, works really nicely. It's just adding on that tiny little bit. So if you can imagine at 100 miles an hour, it will be showing 102. So at 50 miles an hour, it will show 51. It's a tiny little amount, but it gives you that kind of safety buffer. And there's also a requirement for certain country safety standards. Here in the UK, we have to over-report ever so slightly. So our full ratio, let's call it conversion ratio, is the scale times by the safety buffer. And by doing those two things, we can just have one number that we need to multiply the incoming number by. So if the incoming number is 6,000, we times it by the scale, which will drop it down to 60. So that'll convert it from that 6,000. When the 6,000 is coming in, we'll reduce it down to 60, and then we'll give us that tiny little bit of 2% safety buffer. So that'd be like 61 and a bit. But right now, I haven't processed the bytes that have come in yet. Let's do that, and that's what these accessory functions are for. So these kind of things here, basically just shifting byte values left and right so that you can either move the position of a byte relative to one another, so making a big or a little endian and seeing how that changes the overall number, or you can use the bit one in order to extract a single, a 0, 1 bit from a byte. So how we use this is we need it to return a 16-bit int. We need to call it what it is. So really it's the raw value. So the raw value is the process of the endian. We want to pass it the most significant byte first. So that's our speed most significant byte, which is actually byte data. And then in square brackets, the position of that most significant byte. So 1. And then the same again, the least significant byte. So we're going to get back from this process endian the value of this endian swapped, if necessary, pair of bytes. We've not worried about converting it. We've not worried about the scaling factor or the safety factors or anything like that. This is just the raw processed data that's coming from the car, which is why we keep it, a bit separate. So then we actually want to manipulate this value into a value that we're going to use. Again, for now, because we're multiplying it by floating values, this will be a float. The float is raw. Let's say what it actually is right now. Kilometers an hour is equal to the raw value times by the conversion ratio. So that conversion ratio, like I say, knocks it down by a factor of 100 and adds the safety buffer onto it, which gives us a raw kilometers an hour still as a float value, because it's going to be like 62.4 or whatever it is. Now, you might want to display your speed in fractions. If so, this is the information that you would then be sending onto your screen. I don't want to display my thing in fractions. I like having whole numbers in the middle of the screen. So what I'm going to do is round it to the nearest number, but also I need to do the conversion from kilometers an hour to miles an hour. And then we want to put that into our sending data structure over here that we've named. So sending data speed miles an hour. So then our final conversion will be a uint8 again. It's going to be final miles per hour is the raw kilometers per hour times by our, let's call this actually miles per hour ratio, times by our miles per hour ratio. So that gives us a value which is, taking like 62 kilometers an hour and changing it to 40 miles an hour. But like I say, I don't want it to be a float value anymore. I want it to be a round integer number. So we'll just do standard round, which will then round it to the nearest value. Finally, we want to put that value that we've now successfully, manipulated down to into our sending data. So we put sending data dot, and its speed miles an hour is equal to the finals miles per hour. So now, as it refreshes every 10th of a second, this process speed gets processed. It calculates the value. It saves it in this data point. and that data point is getting sent by ESP now every 10th of a second. So that first one, speed miles per hour, would be populated. The rest of these would still be blank, but we can, fill them all in now. That is definitely the most difficult one of these to understand, the processing of the big and little endians. The other ones are much simpler. I thought I'd start you off with the tricky one. Like, let's take RPM, for example. We duplicate this and do process RPM. And again, we'll just put a case in at the bottom down here for processing RPM. And that happens when the ID, which we already again know is 23D. This one is a much simpler version because we don't have to do like the safety conversions or the miles per hour ratio. There is a scale. If you remember, we have a scale of 3. So I'm multiplying the number by 3 in order to get our real value. Then our most significant byte was, if you remember, it was switched the other way around. So our most significant byte was 4, our least was 3. So let's just update these values here that we know what we're talking about. This is our RPM. And we've got a scale. Also, this is RPM least. So our raw value, again, is this process endian, which we've passed through to this helper function, which is going to return with our value, which is, like I said, going up and down to about 1500 in our example. But it's already a whole number. It's 0 to whatever. It's not got a point something. There's no floats. So we can just make our scale an int, make life a bit easier. So our int 16 final RPM is equal to our raw value times by our scale. And that's it. So in this one, all we're doing is taking in the 2 bytes. We're finding out what the return value is based on the shifting of the bytes around into a little endian format, and then multiplying that number by our scale of 3. So then we do our sending data of RPM is equal to final RPM. So that's that one ready to go. What about a single byte? That's nice and easy. In fact, that's the easiest one. And the single byte example that we're looking at is coolant temperature. So let's process coolant temp. And that is on ID 551. Start it the same up here. So process coolant temp. And this one is much, much easier. All we need to know is what is the byte number, because again, there are 8 bytes here. Which one do we need to be looking at? And for this one, it is byte 0. And is there any modifier, anything that moves that value up or down? And in this case, there is. So it's modified by -40. So like I said, it can bring 0 down to a -40 value. So I might just, for the sake of readability, want to do integer of the byte position is 0. So our final temp is simply byte data that has been sent in. So that's all 8 bytes. We're looking at the position of the one that's been sent through. So byte position 0. And that would give us the number. But then we're just manipulating it by -40. So we could just do -40. It's a simple way of doing it, which will give us our final temp. So then we need to have one of these sending data allocations. So sending data of the coolant temp is equal to final temp. So that's a single byte one taken care of. Really easy. That's by far the easiest one. Lastly, we have when we're listening out for a single bit, whether or not that bit is on or off, is true or false. So we're going to add in a new case. And this is the case when it is 60D. And this one is for processing our indicators. And as I was saying, each one of those indicators, left or right, or then both, is a single bit being turned on or off within a byte. So we need to identify which bits that they are. So the left bit is actually bit 2. And the right bit is bit 1. Oops, I made a mistake here. It shifts from the opposite direction. These ones are actually bits 6 and 5 respectively. We'll look at this in a closer detail in a later video, but yeah, it should have been 6 and 5, not 1 and 2. And the particular byte that we're looking at, byte position, is byte 1. So our entire byte that we want to get is, first we'll filter out exactly which byte it is. So byte data based on the byte position. So that will give us just that single byte. So then we need to process it to get the 1 or 0, the true or false, the on-off state of a single bit. And that's why I've created this process bit function that just returns a bool, whether it's true or false, whether or not that thing is a 1 or not. So the bool is indicator left on is equal to process the bit, and we need to pass it the byte. Oh, yeah, so single byte. There we go, pass it the byte, and we pass it the position. So indicator left is check out that position. And then we can do the same with indicator right on. Right on. Which means that these two things will now hold a true or a false, depending on whether or not those positions are 0 or 1. And again, we just need to save those into our sending data. So sending data indicating left is equal to indicating left on. And same with right. With that done, we just make sure we've made no mistakes and that all compiles. This is it. This is going to go through, is going to filter out based on the IDs, process the information that we want, and then save all of the correct bits of information into this sending data structure. Then that sending data structure is sent off 10 times a second by ESP now into the world, but left, right. Whoops. Thank you. It's always a mistake. You can't do it perfectly every time. And it's going to broadcast that out into the world, more specifically to this MAC address that we will put in there. You don't need to see the MAC address on my boards. But yeah, it will send it out, and that board will be targeted to receive this information. Once we've confirmed that this all compiles correctly, can upload it onto my board and then move on to the next part, which is creating the screen and actually ingesting and using this information. Using LVGL and designing things and making things all look a certain way is a big old job. So we're not going to go through the specificities in this video of actually how we create labels and all that kind of stuff. I'm going to just put this example, simple code online, and you can look at it and, you know, change it however you might want. But on the screen, we have a few things that we're going to be utilizing that incoming data for. And I'll show you how we then take that data and update the values accordingly in like a robust way. And what we're going to show is the speed, which shows in the middle of the screen at all times, and then just updates based on the, you know, incoming miles per hour. We've got an F1 style RPM gauge at the top, which highlights different values based on the RPM. That obviously you could use an arc, or you could, you know, put the value in as a numerical value on the screen. We're doing this because it's just shows you can do different things with the information than just write out the number. And we've got an indicator left and an indicator right, which light up at different sides of the screens using a couple of icons that we've used in LVGL. All pretty simple. So this is a simple bit of code that I created. We're not going to dig into the weeds of how to use LVGL or create a label or put icons on the screen. I have other videos about that if you want to take a look at them, and we do have more of them coming, but let's just take a look at the structure of it and just see how everything is made. It's pretty simple. We do have the typical setups, LVGL drivers, CANBus driver, because my board does have onboard CANBus, setting up the Wi-Fi in the ESP now, a couple of fonts, some colors that we've allocated, all just kind of like normal board setup stuff. We've got a few values here, which are some things we're going to need to do comparisons against for which lights come on as part of the F1 style light up thing. We create our screen, we create our various components. So we've got the speed value, the unit, which is miles per hour written below it, our 6 dots, and then our left and right indicator. Got a few different styles. So the style of the 2 icons, the style of the speed thing in the middle, and the style of the label, the miles per hour label. We initialize Wi-Fi. When we initialize Wi-Fi, we initialize ESP now, and we register the callback, which we'll go into in a second. Then we initialize a bunch of drivers. These are all the drivers that I have created and set up for my specific boards. Like I say, it will work with the WaveShare 2.1 inch, but you will need to change the pins here. I'll put a note in this file before I upload it to the repo, just saying which pins you'll need to change it to if you're using the WaveShare board. Otherwise, if we just go right to the bottom, what we do on the setup is initialize those drivers, initialize the style, initialize any initial values. We haven't done that yet. We're going to in a second. We build the UI, and then we set the backlight of the screen to 100. That make initial UI creates the screen. So we technically have 2 screens. We're only using main screen, so only worry about that. And then we make the screen UI, which pulls in all these different LVGL components. So we create a speed value, a unit, the indicator left, which is a left symbol, the indicator right, which is a right symbol. And then this like create RPM bullet is just a shorthand. I didn't want to repeat the same code 6 different times. So it just says the size of the bullet and then what the X and Y offsets are. And I've just created a helper function that creates all of those. What we're really going to be interested in is how do we receive the data from ESP Now and use that to appropriately update all of these things, whether they're showing or not, if their colors change or if the values change. If we were using hardwired CAN, like direct into this board, we wouldn't actually need the ESP Now stuff at all. We could just come down and that code that we created over in the sender, this stuff, we just move it here. And instead of having to then, filter it and broadcast it, we could just pull the information we want out straight away from the CAN and do it on the board. But we're not using the direct CAN, we're using ESP Now. So there are a couple of other things we want to bear in mind. And one of them is the fact that ESP Now can be very system intensive. If you bombard it with too much information, it'll just stop LVGL working in a particularly nice way. So we just want to be careful with how often we're pinging data from it, which is why we've limited it at the moment to 10 times a second. So the general process is what we're going to do is we're going to be listening out for any information that comes in through ESP Now, which is done through this callback function, this on data receive. The incoming data here, that is just the flag. Remember I said we use that flag to determine where data is coming from. So if that flag is 0, which is what it will be when it comes from our CANBus sender, because we sent that flag as 0, then this is what it's going to do. And it's going to take the incoming data that's coming from ESP Now, and we're going to want to copy that to our own structure, which we've called ESP Now data. And if we scroll to the top, it uses structure data, which we need to define. And like I said, the incoming data and what the expected data is need to be in the same format. You need to have the same setup. So we'll take the setup from the sender, copy it into here, and that's it. That's good to go. So what that means is ESP Now is going to be sending in the data in that format, and it's going to copy it to the local thing. So as soon as new data comes in, ESP Now data dot speed is going to have the value that's come in from ESP Now. The thing is, we don't want to process that information as it's pulled in and received from ESP Now, because it will cause massive slowdowns in how fast it can process this stuff. We want all the timings and all the updates to be handled by LVGL. So all we do when we've copied that information from incoming data to this ESP Now data is set this data ready flag to true. And that's it. It goes in, copies the data, sets the flag, and disappears. And that's it. It's in and out of ESP Now really, really, really quickly. Then in the loop, if that data is ready, we just print that ESP Now data is ready. We don't need to do that. But we're going to update our values and then set it back to false. So if data's not coming in, we might not update anything. And that's good because it reduces the system resource. But as soon as data's coming in, we update our values, set the flag back to false, and then wait again for more new data. Just happens to be doing that 10 times a second. So the big thing we want to work on here is this update values function. And this is where we want to put our logic to say what is happening on the screen. And I find it's easiest to separate it out into different things. So we're going to update the speed. We're going to update the RPM, and then we'll update the indicators. Just means that as we're building this stuff, we can do it in small chunks and just make sure everything is working correctly. First and foremost, though, at the moment, the indicators are on. And the indicators probably aren't going to be on. That's not going to be its default state. So we can start up, when we do our initialization, we've got a values initialization. So we can do an ESP now data dot indicator left. It starts as false. And similarly, indicator right. And when that's happened, I can then do an update indicators, which is what I've just been doing, which will force an update based on what we're about to do. So let's start with that one. Let's start with the easiest one and update indicators. So this one's dead simple. It's basically changing the left or right opacity from 0 to 100 depending on a value. Because it's a text element, really, even though it's a symbol, we can just do LV set the style text opacity. We're going to set that to, I called it indicator left, and we'll set that to LV opacity cover, which is basically a shorthand for 100. Or you could just call it LV opacity 100. And then 0, which will set it to the main part of the thing. Else, so if indicating left is false, then we set the opacity to 0. And then similarly, we'll do the same with right. So now, as this function updates, and like I said, this is going to be updating 10 times a second. So update values is going to be updating 10 times a second. And it's going to say, is this value, this stored value, 0 or 1? Well, is it true or false? Because it's a bool. And if it is true, then we set the opacity to 100, which means it's showing. If it's not true, then we'll set it to hiding. So this will take care of the indicators. That's that done. Made a small error here that it's failing because I did the update indicators as part of the values initialization. So it's trying to update the values, but they don't exist yet. Stick at the end of the setup. That'll do it. Right. So just like that, indicators are done, values are working, and they start off. So then the next easiest one is updating the numerical value of the speed that's coming in. Similarly, we want to have this update speed function. What this wants to do is take the incoming speed value, and it's going to be as an integer. But when you set text as a label in LVGL, you can't set it as an integer. It has to be converted to a character string. So we're just going to take the number, convert it to a character string, and then set it to the current value of the label. Dead simple. So int incoming speed, and that's going to be the ESP now data that we've just sent in, and it's the speed in miles per hour. So that gives us that value. We'll need to set up a character, so just speed label, and considering is always going to be 3 digits maximum plus the terminating digits, which make it 4, which will make sure it's big enough to hold everything. Easiest way to do this is to do sprint F into the speed label, D, and then the incoming speed. That'll set the incoming speed, which it knows is an integer, and it's going to set that into the speed level maximum of 4 digits. And then finally, if you come down to where our speed is, and here's where we set the text, it initially starts as 0. We can just copy that. We'll just set that value to be speed level. That's speedo sorted. Easy peasy yet again. So, like I said, every 10th of a second, this value is being updated. We're resetting it in the loop, and then it's converting whatever this integer value is to a character string, and then setting that character string to whatever the label is. And finally, the RPM. lights, the F1 style RPM thing. This is going to be the one that's just a little bit different, but again, not complex. All we're doing with this one is saying, is the current RPM that's coming in above a certain value? And if so, switch on the lights. So I want the outside ones to come on amber when we hit this first threshold, which is 3,600. Like I know in my car, the advertised optimum change up point is 4,400 RPM. So if I'm at 4,400, I'm bang in the middle of perfect time to change up in order to get maximum acceleration. So my ideal min and ideal max, I've set that as 400 RPM either side of that perfect point. So if I can shift up in that 800 RPM gap, I'm kind of in the optimizing area. So I want my lower, so my amber, my get ready, it's about to be in the right RPM, to come in another 400 below that. And then my red line is at 6,600. So I want to have it that the outside ones go amber at the 3,600. And then the next one in goes green at 4,000. And then if we go above that, the inside ones go red. And if we hit the red line, all of them go red. So it's like a warning. So this RPM thing is just going to be basically checking the incoming RPM versus the RPM values that we set, the constants that we set, and then changing the color of the dots according to whether or not that threshold has been passed. What we'll do is we'll set a color. So LV color type. So it's a standardized type used by LVGL. And we'll do bullet 1 color is equal to palette dark gray. And dark gray is my default color that I've got them set to. Let's do that for all three. So the default, assuming that they're off, they want to be dark gray. Then we need to have a set of if statements that say, is it past a certain threshold? If so, the color changes for 1, 2, and 3. And it's 1 on the inside, 2 in the middle, 3 on the outside. So the highest priority will be red line, because if we're over red line, all of them are red, and that takes priority over everything. So if the RPM data that's been sent through, if the ESP now data.rpm is greater than this red line value that we've set at the top, so RPM red line, then all of these become red. So we can just do it like this. So that means by having this one first and then putting everything else in an else around that, the other option, means that RPM redline will always take over. It'll always have the highest priority, which is great. Then we also want to check if the RPM is greater than the entry level one. So the entry level one is RPM lower. If it's greater than RPM lower, then the outside ones, bullet 3 color, will be, I said, amber. And because these are 3 independent things, we just check them all independently. So if the RPM is greater than whatever I called the next one, ideal min. So if it's in the ideal range, then bullet 2, the middle ones, become green. And then if it's above the max, then the inner one, number 1, becomes red. So this will just change those variables to the correct color. And then after we've done all that, we need to set the background color of that little bullet object to the right thing. So it's LV object set style background color. And they're called like RPM something or other. RPM level 1 left and right, and level 2 left and right, 3 left and right. So level 1 left will be bullet 1 color set to the main part of the element. So we just need to repeat that 6 times for 6, which gives us this. So outside ones, level 1 left and right, set to the whatever the color is. Same with the middle, same with the end. So assuming I've made no mistakes here, which I don't think I have, what this will do is, like I say, listen to ESP now, sending in all that information. It will get in and out of the callback function from ESP now really quickly because all it's doing is setting this data ready. Then LVGL is going to be updating really quickly with this data ready false true flag thing, updating the values, and then doing these updates 10 times a second. So the speed will update, the RPM will come in, and the lights will light up, and the indicators will come on left and right, depending on whether that value is true or false. So if I upload this to the board, now if I take both the board and the CANBus sniffer out to the car, put them in, we should be able to see all of this working. So let's go and do that. So here it is in the car, just precariously held for now. We're going to create a proper solution for holding these temporarily in the car while we're testing. That's coming very shortly, but see the RPM gauge at the top, speedo, and there's no indicators. It's just plugged into the lighter socket for now. And we have the broadcaster down here, which is hooked up into the laptop. There was actually a problem, this processing of the indicators. I'd put the bits in incorrectly, the bit positions, so they should have been 5 and 6. But other than that, everything seems okay. So let's take a look at it. The car's not currently started up, but the indicators should still work. So if I go left, there's left. And we can see it's actually in time with the indicator from the car. Now if we go right, that one is over on there as well. I got the car started up, and then we're hoping that this RPM comes in. I don't particularly want to redline it whilst it's cold, sat on a drive. It's not very neighborly, but let's get the RPM up. You see our RPM is working. What about speed? Well, in order to do that, we're going to need to drive. So let's do that. Okay, let's go on the road and speedo down to 0 as I stop. Apologies for the bouncy video that I'm sure we've got here. This is all quite precarious. I got my phone stuck to my window. It's not ideal. If anyone from GoPro or similar is watching this and wants to sponsor me, I will happily accept that. Driving leisurely, so the threshold for the RPM lights doesn't come in. But if I gun it a little bit down this next road, we should see everything working together. So you'll see I'll indicate left. Let's slow down, let the car in front get ahead. There you go, left indication. Drop down to second. Slow down. And we'll speed it up the RPM. So there we go. In one session, we've been able to figure out the information we want to take from the CANBus, filter by it, and process it according to the kind of data it is, whether it's a bit, a byte, or multiple bytes. Broadcast that via ESP now to our screens, and then use that information on our screens to change, whether or not an icon is showing, the way things look, or the values, or whatever it might be on the screen. What you can do from here is then start to build up your own displays, whether it be, numerical values like we've done, or things that are contextualized like our indicators, or an arc, or a meter, or whatever it might be, and use these similar filtering processes that I've got available in this demo code to update the value of those things accordingly. Like an arc, instead of converting the integer to a character string and then setting that to the label, you just use that to set the numerical value of the arc. It's pretty easy. So once you've defined a process like this of how you're taking the information in one end and processing it out the other end, the rest is just fluff. It's pretty easy. It's just how you decide to design your screens. The actual information transfer and processing is actually pretty simple. So like I said at the start of this video, if you've watched this through, I'm pretty sure you're probably setting up gauges like this for the first time. But if you are coming to this completely blank and fresh, hopefully that's helped you realize what we're doing isn't all that hard for now. Obviously, when we start talking back to the car, that's a whole different thing. But the process of removing that information, filtering it, manipulating it, and displaying it not all that bad. And hopefully that'll help you get started with your projects. Like I said, the code for this is all going to be available on the repo below. I've got the blank one and the completed one. So if you want to just play with my final one, you can do. Obviously, you'll need to change the sender values based on whatever your CANBus IDs are. But the rest of it, the visual element, should be fine and should work if that's what you want to use. Otherwise, there's, like I say, basic ones which you can use for your own setup and, as a starting point. If you've got any questions about this process, obviously feel free to stick them in the comments below and I'll try and help anybody out as much as I can. Otherwise, if you want to talk to me directly and a load of other people who are really good at this stuff, you can head over to my Discord. There is a link in the description. We've got hundreds of us over there now, all talking about our various ongoing projects. And it's a really awesome little community, both of hobbyists and professionals who are building digital dashboards and a bunch of other cool stuff. That's it for another one. Big, long, intense one, this one was. Whatever you're doing with the rest of your day, folks, have a wicked one, and I'll see you next week, same time, Wednesday, 2 p.m. Take it easy, peeps. Bye-bye.